Hi, it's time for another math easy solution. Turn to discuss further into applications of integrals and now look at probability. Basically, calculus plays a role in the analysis of random behavior. Well, suppose we consider the cholesterol level of a person chosen at random from a certain age group, or the height of an adult female chosen at random, or the lifetime of a randomly chosen battery of a certain type. And such quantities are listed above here. Yeah, these are called continuous random variables because their values actually range over an interval of real numbers, although they might be measured or recorded only to the nearest integer. So they're continuous in the sense that you can't actually measure it exactly. It'll have to be through a range, and if you were to graph them out, you could draw it in a continuous function. Basically, a continuous random variable is a random variable where the data can take infinitely many values. Then I'll explain this further. It is also impossible to measure exactly any of the values, but can estimate it based on how accurate your measuring device is. The opposite of this is something like a coin flip, where it's either heads or tails and no in between. And part of the basically another continuous variable is if you were to look at the height of a person, for example. Height, for example, let's say you are 1.7. If you were 1.7 meters tall, you can't say you're exactly 1.7 meters tall, because that would mean you have exactly 1.7 all the way to have unlimited zeros accuracy, which is impossible, and there's no way to measure that. So this in fact goes to infinity. So that's why this is a continuous random variable. And also, if you were to see, let's say, the difference between 1.7 and going to 1.8 meters, 8 meters in height, there's again infinite number of possibilities, because again these are all infinite across. So you're going to have 1.710000, etc., 1.75000. So there's infinite in both ways. There's impossible to exactly measure at one point. Yeah, so instead of finding the exact number, instead we might want to know, let's say, the probability that the blood cholesterol level is greater than 250, or that the probability that the height of an adult female is between 60 and 70 inches, or the probability that the battery we are buying lasts between 100 and 200 hours. So let's look at the battery case. So if X represents the lifetime of that battery, and we'll just use this as a continuous random variable because it's just a lifetime of battery, we denote this last probability as follows, basically. P of, now we have, and this last probability, which is this one right here, for a better arrow. So we could write this like this. So probability, we'll use a P, and then 100 less than or equal to X greater than or equal to 200, because you can include the 100, 200s in there. And then we'll write this probability as a range, and we'll call it P of, and then 100 less than or equal to X less than or equal to 200. Now this probability right here, we can interpret this probability as the number, or actually better than writing the number, as the long run proportion of all batteries of a specified type whose lifetimes are between 100 and 200 hours. In other words, we're going to need to do an experiment on many batteries, and then we'll use the average values as basically the basis for our probability. Yeah, again, in other words, if we were to run tests on many batteries, we'll use the frequency or number of batteries with lifetimes in any given range as the basis for the probability of a battery lifetime in that range. So again, probability is based on basically experimental evidence, or just running tests many times. So the probability depends again on what you're likely to see happen by running a bunch of tests and seeing what happens. For example, in our case, let's just assume out of 100,000 battery tests, 80,000 batteries have a lifetime between 100 and 200 hours. Since 100,000 can be assumed to be adequately large, again, it's an assumption we're doing, and that's pretty much whenever you deal with scientific experiments, you're going to have to assume stuff like this. And again, this seems reasonably big. We can use the proportion of 80,000 batteries having lifetimes between 100 and 200 hours to the total 100,000 batteries as a probability. So again, we're going to use the proportion, and we're going to consider it as the probability that any given battery would have a lifetime between 100 and 200 hours. And again, since it represents a proportion, probability naturally falls between 0 and 1, which is what we're used to writing, any proportion. And again, in this case, we're just going to be using this experimental data, which we just assume it's true. So the probability 100 less than x less than 200, there's a lifetime of the batteries between 100 and 200 hours, is going to be, well, we're just going to assume based on the experimental evidence, which had 80,000 batteries with this lifetime divided by the total number. So 80,000 divided by 100,000. See, all the zeros cancel. We're going to be left with 8 over 10, which is just 0.8. And again, this equals to 80% if you write it as a percent. Let's write this neater. And now notice again in this above example that we used a range of lifetimes for the probability, and if we rather were to find the probability that a battery has exactly 150 hours, the probability is actually 0, as explained above as well. And again, this is because there's no way that a battery has a lifetime of exactly 150.000 and infinitely number of zeros. There's no way of even measuring that. Thus, instead of finding the probability of exactly 150 hours, we instead could look at approximately 150 hours by again using a range, but using a small range. So again, by instead of finding probably that has a lifetime between, by instead finding the probability that a battery has a lifetime between 150 to 150.01 hours, which is pretty small. Let's assume that the answer in this case is just 2%, or in our case, again, all these probabilities go back to the experimental evidence, which in our case this is assumed to be, well, 2%, or which means 2,000 batteries having a lifetime between 150 and 150.01 out of 100,000 total batteries. And we can write this as probability 150 less than equal to x less than equal to 150.01. And again, we're using the basis of the frequency interpretation, or the long run, 0.02, which equals to 2%, which we are assuming the value. So basically what this means is approximately 150 batteries, percentage chance of that is about 2%, getting approximately 150 hours lifetime. But let's say we wanted to get a bit more accurate, and we want to find the probability that a battery dies between 150 and 150.001 hours, or between 150 and 150.0001 hours. So again, trying to find it more accurate to it. In these cases, since we are considering such small intervals spaced out by 1/10 the previous interval, we can just assume that the probabilities are also going to be approximately 1/10 the previous probability. So again, we're assuming it's really small, so that the amount you decrease this interval will also decrease the probability in a linear fashion. So again, 1/10, 1/10. But again, that's just an assumption. So what happens here is, so if we were to write 150 less than x less than 150 for the second interval, which has slightly smaller, so 1 decimal place away, this equals 2, or this is roughly equal to, and now we're going to go 0.002, so we just divide this by 10, and this equals 2.2%. So going even further for the next interval, 150 x 150.001 is roughly equal to, then divide this by 10, this is going to another 0. This equals to 0.02%. And as you can see, the more accurate you want the lifetime to be closer to 150, the less percentage chance you're going to actually get that. And in this simple case, the ratio of probability of a battery dying during the interval divided by duration of that interval is approximately constant. As you can see, we're just moving it by decimal place. And what I mean by this ratio, whenever you're dealing with small intervals like this, I'll write this ratio. Probability of a battery dying during an interval, I'll write this as P of, and then, well, in our case, we're going to have 150 less than x less than, this is 150.01, divided by that interval, which is 150.01 minus 150, which equals 2. And again, so this probability is over here, 0.02, divided by this interval, which is, well, the difference, that's just 0.01. Divide this out, all the zeros cancel, we're just left with, and again, this is in units of hours at the bottom, and the top is the probability, just a proportion, it has no units, so this is hours, and we're left with, write this out, 2 over hour. Or you could write this as 2 hour, and then power of negative 1, or the inverse of the hour. So yeah, those are the units for this ratio. And now let's just look at the last case, which is at the smallest interval over here. So this would be, again, it's gonna be constant as well. So 150. Let's write this 5 better. Less than x less than 150.0001. This equals 2, and divided by, again, 150.000, I think is one more 0, 1. Was it one more 0? So that's too many zeros, just 3 zeros, minus 150. So now we get right here 0.0002. So it's 1, 2, 3 zeros divided by, again, the interval is 1, 2, 3, like that, which equals 2 over hour. All the zeros cancel. So as you can see, these are constant. So it's approximately constant, again, because we're dealing with such small intervals. Yeah, and we can just generalize. So thus, if the interval delta x is small, we can assume that the above ratio is constant. And in general, what we'll have is, yeah, for this case, so P of 150 less than x less than equal to 150 plus delta x. And now divided by, well, that interval is going to be, again, this is 150 plus delta x minus 150, and that's just canceled, that's just a delta x below it. So this equals 2p of, this is for completeness sake, I wrote this down, so this equals to delta x. Well, actually, I'll just erase that up. So yeah, this is basically cancel, this is delta x. So again, the probability of it falling in this interval divided by this difference in this interval right here. And in this case equals to 2 over hour, which is, well, constant. I'll just say roughly constant. Yeah, now we could basically rearrange this above formula to get the probability of a battery with an approximate lifetime of 150 hours. So just rearrange, just move the delta x on the other side. So 150 less than equal to x less than equal to 150 plus delta x, so however small you're looking to find it. And then this equals to 2 over hour, which is the units. I'll just write actually like this, 2 times delta x, and the hour and the units are in hours. Let's write that here. 1 over hour. Actually, the units actually cancel here. So this is 2 over hour times delta x, which is an hour, so it cancels and you get a probability. I'll just write it like that. Yeah, so what this means is we can use this ratio 2 over hour, which is again experimentally derived or estimated from a bunch of, for thousands of experiments for whatever case you're looking at or whatever random variable, and we just multiply by this interval right here to get an approximate probability. Now let's look at an extreme example of this case. For example, if we wanted to find the probability that a battery dies at 150 hours but accurate to 1 nanosecond, and 1 hour equals to 3.6 times 10 to the 12 nanoseconds, or ns. The probability is roughly, well, we could write this as 150 less than equal to x less than equal to 150 plus 1 ns. Let's write this neater, 1 ns. This equals 2, roughly 2 over hour, so using that same experimentally derived formula, so 1 ns, and it's in hours, the units, so we're going to have to multiply, convert it to hours, so 1 over 1 hour and then cancel ns by writing 3.6 times 10 to the 12 ns. Yeah, now if we were to plug this into the calculator, we get, well, 2 divided by 3.6 times 10 to the 12, that's about 5.55, 555, etc., all the way going to infinity, e to the negative 13, or this is just another way of writing times 10 to the power of negative 13. So this is 5 we'll just round out to 5.6. So this roughly equals to 5.6 times 10 to the negative 13, and the units cancel. This is a probability, this is a proportion, and this value equals to, if you were to get the zeros, well, this, since decimal places is 13 decimal places to the right, and then when you include the 5, so then there'll be 12 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 5, 6, so that's 13 decimal places away. And this, as you can see, it's pretty much, well, 0, roughly equal to 0%. So there's pretty much almost no chance that you're gonna get a battery with basically 150 hours lifetime accurate to 1 nanosecond. That's just not gonna happen. Yeah, actually, in theory, that could happen, but that's like winning the lottery several times. Actually, it's better odds of winning the lottery, I'm pretty sure. Yeah, now this ratio of 2 hour or inverse hour or 2 divided by hour is called the probability density, and in this case at a battery lifetime of 150 hours. And if we were to graph the probability density of all possible lifetimes, we obtain the probability density function. Again, remember that these probability densities are taken from the frequency interpolation or ratio of specific battery lifetimes to total batteries as explained above, and this function is numerically modeled or derived from experimentally measured values. And most familiar probability density function is known as the bell curve, and models many continuous variables pretty well, such as population, heights, grades for school, etc. And let's just assume that the bell curve models are battery lifetimes, a random variable as well. So this density function would look something like this, where that 2 over hour is used as the function. So this is going to be x, which is in hours, and then y, which is in 1 over hour. And then over here we get a probability function that looks like a bell curve like that. And we'll just assume that somewhere over here is our, I'll write this y equals f of x, let's write that. Y equals f of x, it's a probability density function. And then over at this point, this is 150 hours. Yeah, and now at this point, this is that experimentally derived value of, well, 2 over hour. Yeah, and we could just write this part right here, f of 150 hours, which equals to 2 over hour. Now the probability at approximately 150, as explained here, this is 2 over hour times delta x. So if we were to write this out, I'll draw this in red. So let's say it's a distance of delta x like that, and draw this down. So we'll have, what we have here is an area. So across here is delta x, and then this full height is, yeah, so we have an area of a rectangle. This is 2 over hour. So this area is equal to, well, 2 over hour times delta x, and this represents, well, probability. So probability of approximately 150 hours lifetime of the battery. So again, now when this is an area under a curve, and this makes sense when we just expand this and do a bunch of areas at a bunch of different points, we can obviously write it as an integral, as I've explained in a bunch of my earlier videos. Yeah, and again, as can be seen above, the probability that a battery has a lifetime of approximately 150 hours is represented as the area of the rectangle under the curve with width delta x and height 2 over hour. And now that we've established that basically the probability is just can be represented as an area under this probability density function, which is again experimentally derived. Now we could write this in a more general way and using integrals. So now let's look at a more general probability density function to see if we can approximate the probability that a continuous random variable x lies between a and b. So now we're just dealing with just any random variable as opposed to strictly the battery one. So if we have x and it has units, I'll just write units. It could not have units, but in our case, let's assume it does. And then the y is 1 over units of x. So 1 over exact same units as x, like that. And we'll draw the same bell curve just because it's most often used. So this is y equals f of x. And now we're trying to find out if we can approximate the probability that a continuous random variable x lies between a and b. So we'll just do it, instead of really small intervals, really big. A and b. Yeah, now like always we can approximate this by breaking up this interval into n sub-intervals of equal width delta x. In this case we can select the sample point for which value is going to be on the f of x curve as xi star. And this is the value. Yeah, I mean we're going to pick the sample point xi star as the left endpoint just because it is easier dealing with it since I already went over using the left side for our example. So we'll just pick the left side, and again if you see my earlier videos, this xi star could be anywhere in between xi and xi minus 1. And again I'll explain this further. So let's break this up into, let's say from this side all the way to here, this is x1, and then go to the left here, so we're picking the left endpoint as our sample point that touches the curve is x2, and etc. keeps going on and on until we have a general one like that. Let's draw this a bit neater or a bit straighter like that. So this is our xi, and this is our xi minus 1, which is at the curve right there. And this value is f of xi minus 1. And it goes all the way to xn, which is here, xn equals to b, and this part right here, x0 equals to a, xn equals to b in our case. And then this last point is going to be something like this, where this value here is xn minus 1. It's always the left endpoint that touches this curve. Anyway, so, and then let's put dot 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 for just a bunch of rectangles. Yeah, so now let's look at this case right here. Now these are again all separated by delta x. I mean, they all have width of delta x. So let's look at this area. So this area right here, we'll call this ai. And again, that just equals to f of xi is the height. I mean xi minus 1 times it by delta x is the width. Yeah, and now since the probability that x is between xi and xi minus 1 and xi is approximated by this area, we can thus sum all these areas to get the overall probability that x lies between a and b. Again, what I mean is this area right here, ai is equal to, well, the probability that you have x right here is greater than equal to, let's write this, x is greater than equal to xi minus 1 and less than equal to xi minus 1 plus delta x, which is, well, just simply xi. Yeah, I'll just write that above here. This is just equals to xi minus 1 plus delta x. Exactly as I went over in the battery lifetime example. So if that equals that, so now when we sum it up, so what we could do is that's the probability that goes somewhere here. Now if we find the probability that, well, from x1 to x2, from x0 to x1, sum all these up, then we get basically probability that all of this happens, which is going to be, well, probability from a to b. Because again, these are all proportions of, that is less between 0 and 1, so when you sum it up, again, they'll be under 1 for probably a to b. So what we'll get here is p of a less than equal to x less than equal to b equals 2 roughly. Now we're just going to sum this up. I equals 1 up to n is sub-intervals, And now this is going to be, and this equals to f of xi minus 1 times it by delta x. And I'll put that in here. So again, we're going to sum all these up. Like that. This is I minus 1. Let's write this one more time neater. Okay. And now, like always, you can see this is a Riemann sum. What we can do is take the limit and writing this as an integral. What we end up getting is right here, p of a less than equal to x less than equal to b, with the probability that x between a and b is going to be equal to the limit now as infinite number of these rectangular subintervals. And that they're infinitely small delta x now, because you have infinite of them. I equals 1. F of xi minus 1 all the way to delta x, and writing this as an integral, this equals to the integral from a to b of f of x now, because again xi minus 1 is going to be roughly equal to xi because it's infinitely small delta x, so we could just coincide that, just write it as x, and then dx for an infinitely small delta x. Yeah, and I'll just write this out like this: p less than a, so x is less than, x greater than equal to a, less than equal to b, and now we have this integral. And again, this is just an area under a curve, so I'll just write that it's an area. And if we were to graph this out like this, x, y, so you have x and y, and then you have this curve like that. And again, this is from a, this is all the way to b of the probability density function. This is y equals f of x. And again, for just completeness, just to make sure you always know the units, this is the units, and this is 1 over units. And then this is just an area. So this area is equal to the probability that x lies between a and b. Like that. Yeah, now some more points on this probability density function. In general, the probability density function f of a random variable x satisfies the following conditions. F of x is greater than 0 for all x, because again, probabilities, we're assuming that they can happen, so you have a positive chance, not some negative. I'm not sure what case you have a negative. Because probabilities are measured on a scale from 0 to 1, and that the area under the curve represents a probability or proportion for any given range, the probability that the random variable x is any value, has to be 100%, meaning, let's say you get the height of someone, it has to be a value, not some sort of weird value. So it has to be an actual real number, so thus this, then it has to be 100%. So there's a 100% chance that if you take a random height of someone, you'll actually get a height. And this represents the entire area under the curve. So this means that the probability of anything happen, again, since area is a probability, the probability of anything happening has to be the entire area. And we can write this as an integral as probability that x is any real number, or writing this as x is an element of all real numbers. That's one way of writing it. Or you could also write it as p of negative infinity less than equal to x less than equal to positive infinity. So basically we're taking every single value, and then this would just be our new a and b, so we can just write the integral as negative a to b as the new intervals of f of x, because it's an area, dx. And this has to equal 1, because the total has to be 100%, so it equals to 1, which is, if you're writing in percent, it's times by 100 out of percent. So this equals 2%, 100% equals 1. Yeah, and so that's pretty interesting too. Anyways, that's all for today. If you learned from this pretty extensive introduction to probability, and also eventually get to the integrals part and how to write it as integrals, and to show that even probability is an application of calculus and integrals. Anyways, that's all for today. Hope you learned, and like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.